Okay, let's solve a few problems on chapter 25, electromagnetic waves. The first problem is to give the direction of the missing quantity for each of the four waves listed in the table. So the general rule here is if you have the electric field and magnetic field given, then the direction of propagation, the velocity for electromagnetic wave would be the cross product between the electric field and magnetic field. So essentially, it's just V equals E cross B. So uh, start with electric field, four fingers with electric field, uh, curl to the direction of magnetic field, and the thumb shows the direction of propagation. So let's see. Yeah, here we go. So this is a good sketch. You got the electric field into the page. So four fingers into the page, and you curl towards the magnetic field direction. So you curl up. Yeah, four fingers in the direction of electric field and bend them in the direction of the magnetic field. So using the right hand rule, your thumb shows to the right. So four fingers into the page, curl or bend those four fingers upward in the upward direction, and the thumb shows to the right. This is your right hand rule. E cross B gives you the velocity vector. This is the three-dimensional representation. For two dimensions, once again, it would be E into the page, B is up, and V to the right. Second case, for the second case, you're trying to figure out the electric field, so you still want to figure out the same principle. It's where would you put your four fingers, what is the direction, so that when you curl into the positive y direction, into the page, so that the thumb shows to the right again, because positive x would be your positive I, so it's to the right. So this is the case, V is to the right, and where should you put your four fingers? If you curl into the page, so the answer is you have to start from the downward direction. So four fingers with the field, electric field, so downward, and you curl them into the screen, into the page, which is a little uncomfortable. So, but anyways, four fingers downward, and you curl them into the page direction. And the thumb still shows the direction to the right, which is the velocity vector. Third case is direction of the magnetic field. So you start with positive Z or positive K, and you curl in a certain direction so that the thumb shows out of the page. Negative Y is out of the page. So here we go. Negative Y out of the page is the thumb direction. And you have to start from upward direction this time. So electric field is up, four fingers up, curl them to the right. So that's exactly how you're going to get the thumb pointing out of the page. Four fingers up, curl to the right, and the thumb shows out of the page. Final case. Final case is, yeah, you start with positive Z direction, curl four fingers into positive Z direction, curl towards positive Y direction. So which way is the thumb showing? So positive Z direction to start with. So upward. four fingers upward, and you curl them into the page. And then the thumb shows leftward direction. So the direction is negative X direction, or you say negative I with a hat. Either way, this is the representation for the final case. So right hand rule, same drill as before. Uh, the electromagnetic wave is composed of changing electric and magnetic field vectors. So the direction of propagation is easily described with this relationship. E cross B gives you the V. V is the direction of propagation, velocity, if you will, for the electromagnetic wave. Next problem, we got a light year. It's a unit of distance, very widely used in astronomy because for astronomy, miles, kilometers, even astronomical units are too small to really operate. If you start talking miles, then, for example, distance to a nearby star, it's 4 light years, so that would be like 40 trillion miles. Okay, trillion, not million, not billion. We're talking trillions of miles, and that's just a nearby star. And then we have 100 billion stars just in our Milky Way galaxy, and then there are 100 billion galaxies, actually more than that, but just to give you an idea, we have billions and billions, and you multiply by another billions, and those distances are just out of this world. So miles and even astronomical units, which are units of distance between the Earth and the Sun, one astronomical unit is still not enough to describe how far all those stars are. So light year is a common unit. There is another one. There is a parsec, the parallax of 1 arc second. We're not going to go deep into astronomy. The point is there is a light year, a distance that light travels in a year, and we have to express that in kilometers. So for the distance, we need two things. We need the speed and the time. So how fast does the light go? It's the speed of light. It's a common constant, 3 times 10 to the power of 8 meters per second. So you got your speed of light right here. And you multiply by time, because once again, distance is speed times the time. And the last conversion factor is from meters to kilometers because we want kilometers this time. A kilo means 1,000, so you got kilo for 1,000. And it's the whole year. We don't do years in physics. We do system international, so we need to go to seconds. And we have seconds to work with in the first place anyways. So how many seconds in 1 year? You multiply 365 days. You multiply it by 24 hours, and each hour is 3,600 seconds. So the total is 86,400. So you can see the different colors for those arrows to see which one cancels. And you left with kilometers, and everything else cancels out. So 1 light year turns out to be, yeah, we have million as 10 to the power of 6, billion 10 to the power of 9, and trillion, so 10 to the power of 12. We have, yeah, roughly 10 trillion kilometers. Okay, 10 trillion kilometers, just 1 light year. It's just that's why you don't want kilometers to describe those distances in the first place. Light years are much more convenient units. Next question. What's the speed of light in units of light years per year? Well, it's a definition of the speed of light. It's 1 light year in 1 year. So it's just one. Yeah, It's the distance. Remember, light years is a distance that light travels in 1 year. So how fast will it go? What's the speed of it? Well, it's 1 light year in a year. And now it's the speed of light in feet per nanosecond. Okay, so still the speed of light. We start with the speed of light. This is, by the way, the speed for the propagation of electromagnetic waves in vacuum or air. And you have to get rid of seconds. You need nanoseconds, and nano is 10 to the negative ninth. So if you want the backwards operation, then you have to multiply. So you have billion nanoseconds in 1 second. So seconds cancel, and then 1 feet is about 1/3 of a meter. So meters cancel, and you're left with what you want. Feet per nanoseconds, which is that's the amount. Anyways, a little practice on converting units between astronomical units and system international. For all the formulas, once again, you need the system international. Light years are normally used in astronomy just to describe the distances, like how far the stars are away. Okay, next problem. Got a father and a daughter, same baseball game. Oh, yeah. So you're sitting next to your radio and listen to the game. And radio waves are part of electromagnetic spectrum, so they travel at the speed of light. That's why you call somebody on your cell phone and there's almost no delay, even if you're talking to Australia, because radio waves travel at the speed of light. And daughter is in attendance the game and sits far away, so it's going to be the speed of light for the propagation of the sound. So it's the speed of sound versus the speed of light for radio waves. We're going to compare two speeds and see who hears the home run first, uh, even if you're 100 kilometers away, but on the radio, with the radio station, or 100 meters away, but in live attendance, and it's just the sound that you hear. Speed of sound is 340 something meters per second, and speed of light, we already know, it's 3 times 10 to the power of 8 meters per second. So let's calculate the time for the daughter to hear the sound 100 meters away. Divide by the speed of sound. You can see that it's the distance divided by speed. So distance is this much. Speed is the speed of sound. And it takes about 0.3 of a second, which is pretty fast. But once you compare that to the speed of light, you will see that it's much, much faster. Light travels, what is it? It's millions of times faster. We say, yeah, you can say a million times faster. It's 300 and 300, so that will be 10 to the power of 6. So a million times faster. And because of that fast rate of travel, even if you are kilometers away, you will still hear everything within what 1, 2, 3, 4, 5. So it's like microseconds. See, not even milliseconds. It's even faster than that. So everything travels. So information traveling at the speed of light is capable of producing exchange of data, the data transfer rates without any delays, like noticeable delays. Yeah, and this is another explanation for what you see first and then you hear. So you see the lightning that strikes first, and then a few seconds later, you actually hear the thunder. And there's actually a rule of thumb for calculating how far away the lightning was from you. Each second of a delay between the actual lightning and you hearing the thunder. It's about 1 mile of distance between you and the source of lightning. So if you see the lightning and then you hear the thunder right away, you really want to run away from that place because you're too close to that spot. And you don't want to be hit by lightning. You'll die from that. So sound travels fast, but not as fast as light does. Okay, now we got galaxies moving away from Earth. Yeah, there's a Hubble law, and it's a general fundamental law that describes how all the galaxies are actually racing away from us. Universe is expanding. So everything that you see today will be much further away billions of years later. The universe is expanding, galaxies are running away, and the more the distance to a certain galaxy, the faster it actually is going away, which is something you probably don't expect, but that's exactly what we see in our telescopes. So here comes a galaxy that emits a certain uh, frequency, and it is going away from Earth with a certain speed. Be careful, those are kilometers per second. Convert to System International. So what is the frequency that we actually measure here on Earth? Remember, every time the source or the detector is moving towards you or away from you, you expect a Doppler effect. It's going to be a change in frequency that you measure. There is a example in the lectures about the police radar that measures how fast you go because you're going towards the policeman, towards that radar, the gun that measures the speed, and it can only measure that speed based on the Doppler effect. The formula, yeah, here's the formula once again. We just described it in lectures, but yeah, let's discuss it again. We have the V. Well, first of all, we have the original signal that was emitted by the object. So for this equation, for this case, it's going to be the 5 times 10 to the 14 hertz. That's what's emitted, the actual emitted signal. And then you have the V, which is the speed of light or sound or any other type of wave we're talking about. And Doppler effect is good for all kinds of waves. So this is not sound this time, it's the galaxy, so we're talking light, so it's going to be the speed of light this time. And then there is a plus minus, minus plus. See how I'm showing it's in a very specific way. It's not just a random setup. It's better for you to remember it this way. So top, bottom, top, bottom. And for the top, it's towards, and the bottom is away. And top is towards, and the bottom is away. So if the detector is moving towards the observer, excuse me, if the detector is moving towards the source, then it's a plus. If the detector is moving away, then it's a minus. If the source is moving towards the detector, then it's a minus. If the source is moving away from the detector, it's a plus. So plus, minus, minus, plus means towards, away, towards, away. That's how I like to remember all possible scenarios. So let's see what we have here. The galaxy is receding. So it's the source, the galaxy is the source, and we're sitting here on Earth and we're trying to detect what's going to be the difference, what's going to change. So Earth is the detector and galaxy is the source, and source is receding, so it's going away. So detector is sitting still. There's no plus minus for the detector. Detector is just zero velocity, but the source is moving away. Remember, towards, away, towards, away. So for the away case, you need the plus. So it's zero at the top and plus at the bottom. Yeah, and that's exactly what we have. This is the original signal. This is the speed of light, and it doesn't matter plus or minus because the detector is the Earth, and the Earth is just sitting still. We are sitting here on Earth, and we are sitting still with respect to that galaxy that is racing away. And the source, the galaxy, is towards away. Away means a plus, so we're doing a plus. And be careful, you have to convert to System International. It's not 4375, it's 4375 kilometers. So you have to convert to meters per second. Everything is in System International. Meters per second, meters per second. This also must be meters per second. And you do the math and you get less. See how it was 5, and what you register here on Earth is less than 5. So based on the change in frequencies, you can actually tell how fast that galaxy is going away. So a Doppler effect allows you to do both. Either you say how fast it's going based on the change in frequencies, or you say, oh, because it's going this fast, the change in frequency must be this much. Either way, it's going to give you a good answer. So yeah, Doppler effect doesn't matter light or sound. The only difference would be the speed to work with, the speed of light or speed of sound here. And if detector is going towards you or away from you, the source is going towards or away from you, all of those cases are covered with towards away setup that you see in this equation. Okay. Um, okay. It turns out that human beings radiate electromagnetic waves. Your body emits radiation. Whoa. You are radioactive, literally. And the wavelength of that radiation is about 9 microns. Microns is a fancy way of saying micrometers. Yeah, I have this note here. So microns are just micrometers. If you ever see microns, that's just micrometers. So 9 micrometers is the wavelength. The question is, what's the frequency? Well, wavelength and frequency are connected with a very simple and straightforward connection right here. It's the speed of light, which is the frequency times the wavelength. And using this little equation, you can uh, connect all possible, say, radio waves for your favorite radio station. That 102.7 Kiss FM. What is that 102.7? That's frequency. And those are, by the way, megahertz. So if you want the wavelength of your favorite radio station, just divide the speed of light by the frequency that your car stereo shows you. So what's the frequency? It's the speed of light divided by wavelength given. Speed of light is 3 times 10 to the power of 8 meters per second. That's the constant. And because it's microns, you have to convert those, that it's not just 9, it's 9 times 10 to the negative 6. Negative 6 is your micro conversion. So you get 3.3 10 to the power of 13 hertz. Remember, hertz, once again, it's the frequency, means how many times your wave goes up and down in 1 second. So this is a crazy number, but that's what it is. The radiation from your body oscillates, that wave, that electromagnetic wave oscillates up and down, trillions, hundreds of trillions of times in 1 second. And if you take a look at the infrared, if you take a look at the electromagnetic spectrum, you will see that this frequency corresponds to infrared range, and your body emits infrared radiation. We feel infrared radiation with our bodies also. If like you're sitting next to a heater, then your body can absorb that radiation and you feel the heat what you feel as heat is just your body absorbing infrared radiation. And your body also emits that radiation because we are at a certain temperature, and temperatures correspond to certain wavelengths and frequencies. That's the Wien's law and Stefan Boltzmann's law. All of those laws are widely used in science and in astronomy for sure. Okay, got a television tuned to a certain station, to a certain frequency for best reception. We have an antenna, should be adjusted to have a tip-to-tip length equal to half a wavelength. Okay, half a wavelength. What's the length of the antenna? Well, if the length is half of the wavelength, then your lambda, which is the wavelength, is just uh, times 2. That would give you the length. So you still use the same equation, the speed of light equals frequency times the wavelength, but wavelength is double the length of the antenna. That's just what's given for the optimum receptance. It says length, capital L, is half a wavelength. So length is half the wavelength, means the wavelength is double the length. And you throw in the double length into the connection between frequency and wavelength formula to solve for the length of the antenna and plug in the values. You got the speed of light because radio waves are still light, and TV is also a part of radio spectrum. If you have a cable, a satellite dish, that would be also microwaves, I believe. And it's still the speed of light that all electromagnetic waves travel at. And we got the frequency given. So frequency is given, but you multiply it by 2 because you want the optimum reception and the optimum length for that antenna, which is 0.7 of a meter, which is like a couple feet. Well, that's your real life situation. You've seen those old school antennas. Nowadays, they make it all digital and with amplifiers. This is like a different story and different discussion. Without any fancy digital equipment, you just produce an antenna of this length, and you can watch that particular station the best possible scenario, best possible quality. Now for the intensity. We have the intensity given, and the question is, what's the electric field? We discussed the formulas that connect electric field, magnetic field, and the speed of light. The Maxwell's prediction for the speed of light comes from that analysis as well. And for the maximum intensity, you definitely expect the maximum electric field. And there was a formula. Yeah, that's the formula I'm talking about. You have the maximum intensity. This is not current, this is intensity. And c is the speed of light. Epsilon sub 0 is the permittivity of free space, which is just the constant. And this is the maximum electric field, and it goes squared. So if you want to solve for the field, then it's the radical on both sides, divide both sides by c epsilon sub 0. That's what you get from algebra, and plug in what's given. You have the intensity given, the speed of light is a constant, and the permittivity of free space. Do the math, grab your calculators, make sure you're getting the same values. And for the electric field, remember we had an option for newtons per coulombs because that's the definition, the force, electric force over the charge. But then we discussed the connection between the field and the voltage, the electric potential. So the most common scenario, it's not newtons per coulombs, but rather volts per meters. So it's 53 volts per meter. Using one, two, one, two. Headset turned off. Okay. There's another equation for the magnetic field in case you want the magnetic field from the intensity. So both fields can be easily calculated from that. Last problem. We got a light bulb with a certain power output. Oh, okay, same apparent brightness. The main idea here is do not confuse brightness with luminosity. And luminosity is the power output. Uh, so uh, there is brightness that depends on distance. Okay, you can be closer to a light bulb and it's going to appear brighter. And if you're moving further away, then the light bulb is not as bright anymore. But the power output for the light bulb, the amount of energy that it emits per second, is the same. Like it says 45 watts, that means that that light bulb produces 45 joules of energy in 1 second. So every second it emits 45 joules of energy. And it doesn't matter if you're close to it or further away from it, the luminosity, the power output is the same. But brightness changes with distance. And there is the inverse square law that says that brightness is inverse over distance squared. So do not confuse brightness with luminosity. Do not confuse brightness with power output. Because power is preset, power doesn't change, but brightness changes with the distance. Okay, so how far away, should that light bulb be compared to another light bulb? And they convert the same kind of bulbs that convert with the same efficiency and radiate uniformly in all directions. So this is the sketch, very good sketch to show you what's going on. You got your eyes that register light. Your eyes are like telescopes. They are capable of registering light and convert that into electricity and send electricity to your brain, and your brain analyzes it and uh, tells you what's going on around. So there is a light bulb that is closer but less powerful, less luminous, and there is another light bulb that is much more powerful, like almost 3 times as powerful, but the distance is further away, and both light bulbs at some point will appear the same brightness. So once again, brightness changes. Brightness changes with distance, but the power output stays constant. It's the same 45 watts no matter what, and it's the same 120 watts no matter what. So for the same brightness, that means it's the same intensity that you register at a certain point away from the source. So intensity-wise, it's the same, and intensity is power with respect to the cross-sectional area, and that would be a sphere, and the surface of a sphere is 4 pi r squared. That's what we have from geometry, and calculus proves that. So that's the cross, that's the surface of a sphere. So power with respect to the surface area, power with respect to the surface area. Here we go, cross multiplication, solve for the missing part, and you get 15 meters. So that means that the less powerful light bulb should be at 15 meters, and then uh, the other one is at 25 meters, and you will register the same brightness. Even though they are of different power, you'll see the same brightness. Okay, that's it for this chapter. Next, we're gonna switch to optics, and then other effects for optical, well, optical instrument, optical devices, and then interference and diffraction. So that's it for this chapter.